Hallo in die Runde. Es ist wieder mittwochs um 2 und das heißt für mich inzwischen schon relativ gewohnt, heute ist wieder Webinarzeit, IoT und Open Source Zeit. Bevor wir so richtig loslegen, es fehlen auch noch ein paar Leute, die sich angemeldet hatten, hätte ich eine Frage. Das Thema heute ist eher technisch mit TimescaleDB. Und es gibt den einen oder anderen aus der englischsprachigen Community, der sich das Thema gerne anhören würde. Deswegen die erste Frage, die ich jetzt gleich auf dieser Seite im Poll starten werde. Spricht etwas dagegen, dass wir das Webinar auf Englisch halten? Oder ist der Poll hier? Okay. Das heißt jetzt hier ähnlich wie vor dem Traualtar, sprecht jetzt oder schweigt für immer. Aber sieht sehr gut aus. Then we officially switch to English now. Okay, I will start to share the slides. Okay, the slides are not loaded for whatever reason. Then I will just start the slides on my machine. So our topic for today is, as announced, TimescaleDB, and I hope everybody sees my presentation now. Okay, I will not repeat some basic stuff that we talked about last week, where we had another time series database, so I will skip a bit the basics of time series databases and why you need them, but we'll show some examples later on where you will see why it's useful to have this time series approach and this time series extension. This is the roadmap of things we want to do and we have done so far. We had PSC4X, we had Ditto, we had IoTDB, which is pretty similar in what they want to achieve to IoTDB, but does it totally other way around. Usually I say something about me and my relations to the project, and TimescaleDB really is, from all the projects we have here, I think the project I'm the less involved, so to say. I'm a long-time Postgres user. I follow the TimescaleDB development, I don't know how long now, but very loosely. But I use TimescaleDB and we also use in my company in production. So I can give at least some half-qualified opinions on TimescaleDB and on Postgres as well. Okay, now we start with the introduction to Timescale, and as I'm rather loosely connected to the project, I did not prepare the slides myself, but looked up for a really nice overview of TimescaleDB from Stéphane Fréchette, which is one of the more involved people in the project. I will change my screen now, and you can see the presentation here, so it's publicly available. Okay. So now we move over to the presentation. This is the presentation. This down here is Stéphane, who initially made this presentation. Okay, so I hope everybody sees my screen now. Yes. Is the screen visibly good? Yes. Okay, excellent. Okay, so some of the things we talked about last webinar, time-series data is everywhere, and indeed it's true, especially in the IoT or IIoT area. But starting with the basics of what is Timescale DB. Basically, one thing that's important for us in this webinar usually is open source. At least it has an open source distribution. There's also a non-open source distribution or commercial distribution. And it takes care about fast data ingestion and complex queries. This is, I would say, probably saying here, complex queries is one of the main differentiators in comparison to IoTDB. As TimescaleDB is fully SQL compliant, as it's based on Postgres, but can do some things more than a regular RDBMS in comparison to IoTDB, which is a so to say NoSQL database built from the ground up. It's rather easy to use, as all queries you do are not in SQL dialect, but are fully compliant SQL. And you can not only operate in time series, but do whatever you want to do with an RDBMS, joins, subqueries, window function, aggregates, whatever. It's based on Postgres, so it's fully JDBC and ODBC compliant, and there are tons of tools out there which are optimized for Postgres. pgadmin, for example, PSQL shell. It has, in comparison to regular RDBMS, it has time-oriented features and an API, and it has data retention policies. This is something which is, okay, Chris writes the screen looks messed up. 1 second. So I stop sharing and try to share again. Do you see anything now? I try to read. So I try to share the screen again. Does not work. This is an issue we had last week also. I don't know what's causing it. Then we try something different. Give me a second. I'm back again with another browser now and try to share my screen. That's the wrong one. Well, let's try to do it on this screen then. No idea where this was. Okay, are you able to see my screen now? Okay, excellent. Okay, so hopefully everything works now. So data retention, this was the last thing I was talking about, to basically throw away old data, every time points that are older than 1 year, for example, is something which is rather special in time series usage. Scalability is not so much of a concern for us usually, but if you operate in a backend or in a data center, you want to have some kind of parallelizability, which is usually also easier for time series data than for regular databases. Reliability is an important concern. especially when operating on the edge in industrial IoT scenarios. I personally like to have a Postgres running there as core, as it's so solid. It's over 20 years old. There are tons, probably thousands of bugs already found and fixed. So you won't get no issues with database corruption due to hard shutdowns and stuff. This is a really a good reason for using TimescaleDB or Postgres under the hood, and also the flexibility you get because you can also run your regular application against Postgres in another schema and just have your regular application run there without maintaining two databases. I will try to look in the chat from time to time if there are questions. So the most interesting question about TimescaleDB is the data model. TimescaleDB uses something which is called a white table data model. So basically one column per measurement. IoTDB, for example, on the other hand, uses what they here call the narrow table model. So basically each sensor has its own storage area. Which has its own pros and cons, but the white table model is what maps best to the traditional RDBMS world. The architecture is quite easy. TimescaleDB is implemented as an extension on PostgresSQL. Postgres has a pretty open extension API. So TimescaleDB is a full Postgres extension. So basically, whenever you have Postgres instance running, you could install TimescaleDB at any point in time. And it just adds up several functions and triggers and such things in the background. This also means that you don't lose support of any of the excellent tools that exist for Postgres. Also, for example, speaking about backing up, high availability and these things. Because everything goes through Postgres. The architecture is under the hood is quite interesting. What Postgres basically does is to add another layer to a table. So if you have a regular table, then TimescaleDB converts it into a hypertable, which is a logical table, but under the hood it's stored in many small tables, which are called chunks. So for Postgres, it still looks like a regular table, but whenever Postgres tries to access the hypertable, it is basically the query is rewritten to access the chunks underneath. Basically, TimescaleDB brings in the extension everything that is necessary to integrate the hypertable as regular tables into Postgres. So everything needed for the planner to rewrite the rules and all those things. And these hypertables have one time column, which is a crucial column because the partitioning into the chunks is basically done based on the time column. So you can do some optimizations, for example, to only access a part of the chunks if you know it. If such a value is there, it only can be in these chunks. And chunks in the end are a standard database table as it's written here, but should not be accessed directly, but only via the parent hypertable. And Postgres Timescale also takes care about the indexing of those tables. So it makes no sense to apply an index to a hypertable. This doesn't make sense. It only makes sense to apply indices to the chunks because their data is physically queried from. But TimescaleDB takes care of that for you. Another important effect is single node versus clustering. Most of the NoSQL DBs are meant for scaling because they usually solve problems that come from big amounts of data. So the idea is that you maintain some possibilities or some operations or some guarantees that you have on regular RDBMS, but do not scale for an RDBMS. So you're okay to say I don't need 1 instance, but 10 instances, as long as everything still works. So you get something, but you lose something at the same time because you have to operate 10 systems, for example. Especially in IoT situations, industrial IoT situations, where we have some focus on edge computing, you want to go back to single node operations, as you only have one edge device there, and if the edge device breaks, then you're out of operation. So you don't need high availability, you don't need scalability, but you need good performance on a single node. And this is something that TimescaleDB can provide you, as it comes from a regular database system, which are optimized for single node operation. Of course, modern databases can do sharding or clustering in some way, but they are optimized, and especially Postgres are optimized for single node operation and have benefits like code generation for specific queries and those things that you can leverage again. So in comparison to other timescale databases like OpenTSDB or KairosDB, which are backed by Cassandra, which may thus scale very well, but have very, very bad performance, probably 1 or 2 orders of magnitude worse performance than what TimescaleDB gives you out of the box, because it's optimized for single node operation and not optimized for scalability. Another thing which where TimescaleDB, which is crucial for time series database, is insert performance, and this I will show in a minute in a comparison between vanilla Postgres and TimescaleDB. So comparison between vanilla Postgres and TimescaleDB, one of the crucial things is the data ingestion rate. As TimescaleDB uses this sharding underneath, or this chunking underneath, it can maintain basically linear or constant ingestion speed, whereas Postgres will always degrade when the table is too big due to maintaining indexes, checking constraints, and all that stuff. And the query performance is similar. In the worst case scenario, TimescaleDB has similar execution duration or similar execution speed than Postgres, because it just does a regular Postgres query. In best cases, it can be orders of magnitude faster. For example, due to the chunking, if you have a very simple query with an index on the time, then TimescaleDB optimizes it to only look up the chunk where the data is in, which is a very small table. And Postgres still would need to go for an index, but for a big table, which still is slower. And it brings the time-oriented features, which are not available in vanilla Postgres, or only if you write screen-sized queries. Basically, then you still can achieve everything, but it brings the out of the box with a very simple API, SPI, or SQL integration. Here's a direct example of the ingestion rates between Postgres and TimescaleDB, and you see that for Postgres basically happens what is expected, that the ingestion rate goes down when table gets bigger and bigger. For TimescaleDB, it's not the case, because the hypertable grows bigger, but the physical table, the chunk, still has a fixed size and is limited. Thus, it's nearly constant ingestion rate, because the only thing that comes on top is management of some more tables. But this doesn't really add an overhead. So this is a crucial example where in scenarios where you have to just swallow incoming time series data points, TimescaleDB really helps a lot already. Yeah, this is something which is now similar to what we discussed in the last webinar about IoTDB. You oftentimes have different semantics when working with time series databases. Usually, you want to have some kind of downsampling, or how TimescaleDB calls it, time bucketing. So you basically say, I don't want to have all those millisecond space data points, but give me one average value for each minute, or as in this example, for all 3 hours. So what TimescaleDB gives you is a function, a regular Postgres function, time bucket, where you once give the bucket size, and second you give the time value you want to apply it to. And then this time bucket function basically ensures that it applies, that it throws all time points into the same bucket that are within this 3-hour window, and takes care about all the how to bring them together, where to start offset and stuff like that. This means that in the end you can do a regular group by query. As it is standard SQL, which is read in by the Postgres parser, which doesn't really understand SQL. So you have regular where conditions, you have regular group by semantics. The only important thing is that you group on the bucket, of course, and then you use regular aggregation functions like first, last, min, max, average, whatever you like to do. So this is similar to the group by query from last week for IoTDB, which has a bit different semantics. This semantics here is probably not so intuitive from a Postgres, from a time series perspective, but it's standard SQL, which has several advantages that I will show later on in the hands-on demo. Another thing that you can do is last and first aggregates. This is also some kind of special syntax. This is mostly similar to windowed functions. You can use in plain SQL or in regular RDBMS, because oftentimes you want to have the first value in a time bucket or the last value in a time bucket. And to achieve this, you can also achieve this with regular SQL, but then again you get 3, 4, 5, 6 lines of SQL only to achieve this. So it's way more comfortable to say, okay, give me the last price. It's basically the closing price of each day, as this example says here. And then there are other functions provided by TimescaleDB, which allow you to ease the operations you usually do on time series data. We already talked about that some slides previously. For example, in this example, you drop everything which is older than 7 days. And this is something you often do in time series data because you say, okay, I only want to keep the last week or something. Now these are specialized functions which in the long run help you or make it easier for you to maintain the database. Okay, this is basically, we'll skip the demo from this presentation, let's do our own presentation, our own demo, and go directly to the summary. TimescaleDB over NoSQL, like IoTDB, and probably also over regular database, like using vanilla MariaDB or Postgres. One important thing is that it's usually performs very well on single node deployments. It is totally normal SQL, so you get the full power of SQL. Also, not just a SQL-like looking SQL-like looking DSL. You have a lot of simplicity around the operation because there are millions of tools out there to operate Postgres database, to do backups, to do syncing, whatever. You get a very good query performance, better than vanilla Postgres, because some operations can really be rewritten to be way more efficient. And you can, for example, get native support for geospatial data because Postgres has nice support for geospatial data, and also integrate other third-party tools from the whole Postgres environment. So it's a really, from my perspective, it's a really good compromise. for many scenarios, and therefore something always to consider, because it's just so convenient to spin up a Postgres, or sometimes you even have a Postgres already running, and then it's really convenient to just install an extension there and not basically reinvent the wheel. This is so far the part about the presentation of TimescaleDB. And now we come, let me share the slides again. And now we are basically ready for some demo time. Before I start with the demo, are there some rather general questions about TimescaleDB or some things which are unclear from the presentation I showed? Not yet? Good. So what do we do in the remaining time of this webinar? Ideally, we start some discussion and have some questions, of course. But first thing is we start with TimescaleDB with some simple examples about the table, how to create a table or hypertable. Then I will show you how to do timescale operations in Postgres or in TimescaleDB, which is based on Postgres. And the third thing we come to is one of my favorite Postgres features, the JSONB support, which together with TimescaleDB makes a really nice time series application. So all of the things you will see today are no fixed rules like do it that way, it's best, but are just examples of how we successfully operate TimescaleDB and really try to get the best of both worlds, time series approach, but also having Postgres regular RDBMS. Okay, so now I'll try to share my screen again. Okay, excellent. So I have to switch as my browser does not support several screens, as it looks like. I have to jump between the windows a bit. So the first thing we do is we open up the browser. Let me do that here. Okay, and the first thing we do is we go to the timescale site and get started with the Docker tutorial. So they have a quite nice. Sorry, I closed the link accidentally. So they have quite nice getting started tutorials, where you can get the necessary help and get started with using TimescaleDB. They have the community edition, and the installation site is quite nice. Therefore, I wanted to show it because they have native support for Docker. So basically, we can take this command out here, just copy it to the shell of our choice and get started. I hope everybody sees my shell reasonably well. A bit bigger. So this is the first command we start with. It will start a TimescaleDB container, will bind it to the default Postgres port. We set the environment variable for the Postgres to a password, as the official Postgres container is needed since Postgres 10, I think. And we'll use TimescaleDB on the latest Postgres 12 release. I did the setup with the version on Postgres 11, so therefore it has to download the image for a second. But this should work reasonably well. I want to skip it. Okay, so now my TimescaleDB is running in the background. How can I see that? I go to the database tool of my choice, register a new data source for Postgres. Localhost and port are fine. Default user is Postgres for the container, and the password is password. Okay, and now I'm in. So basically, I get the connection, and you see it looks like a regular Postgres instance here. The only thing which is slightly different, where you can see that we have TimescaleDB installed, is when we show all schemas, then you will see that there are some hidden internal schemas from TimescaleDB, which contain the internal information of TimescaleDB. So which here you see the sequences for the chunk management and all that stuff. But from now on, we just have a regular Timescale Postgres instance and can do regular Postgres stuff. I start with a very simple example, which is partially copied over from one of the Timescale tutorials. And first off, create a very simple table. Just looking if there are questions in the meantime. The table is called conditions because we want to register conditions in a location. That could be whatever. So of course we need the time. The timestamps is a shorthand for timestamp with time zone, which is quite crucial when running or doing operations which are not only run in one time zone. Then we have a text, basically varchar, for the location, and then we have two values of type double, which can be null. So this is the first query I execute, and now I have in my Postgres, in my public schema, I have just refresh databases, and then I should see disconnect, reconnect. Then I should have table conditions. For whatever reasons it doesn't work, but if I do a select star from conditions, we get the result, so it is there. Okay, but now we want to, so up to now, totally plain Postgres, but now we want to do TimescaleDB. So what we need is another command, the function create hypertable. This is a specific function of TimescaleDB. I give it the name of the table, which is conditions in this case, and I have to say the name of my timestamp column, where the sharding or chunking will be based on. So now execute the query, and the result is successful. So now my table is a hypertable. What does this mean? This means if you go to Timescale catalog, then in theory, if it's updated, it's not updated. Okay, for whatever reason. Probably I just restart data grid for a second. Probably works better then. Just a second. Then we should see that it's still visible as a regular table, as data grid basically keeps the regular table, but injects all commands that are done against traffic and reroutes them to its internal engine basically. So let's see what we see, refresh the whole thing. And okay, still not working for whatever reason. So what we would see if we would see all the data is that in the Timescale catalog, it has a list of all hypertables and of all chunks that belong to the hypertables. For now, let me just discard all those other schemas because we don't need them for the demo, and go back to the regular schema public. Okay. So
probably that's an issue with the Postgres version, as I do not have the latest driver, and it's Postgres 12, which is quite new. Okay, but back to the topic. So now I have a hypertable, and what does this mean for me? Basically, nothing changes. I can just insert data in there with a regular insert statement, as it's still a regular table. So I will do the insert statement, and it succeeds, as you see below here in the console. But what I see, if I do an explain analyze in the command, then I see that there is some custom stuff going on. I hope it's visibly. You don't have to understand all the details, but it's an insert and conditions, and then there comes a custom scan. So basically, we see that TimescaleDB here intersects the operation and inserts the data in its own way. And this is also what we see if I do simple select star from conditions, regular operation, where I get the two values I already inserted. And if I do an explain analyze, I will see that I did a sequential scan on hyper 111 chunk, not on conditions, because this is how a TimescaleDB writes the query plan, basically. Okay, so now let me insert some more values. Okay, and now we can start with some time series queries. Before we start, we do again a regular select, and we see I have some queries in it. But now we want to do the same subsampling queries that we did last week with IoTDB. Imagine, for example, a situation where you have millisecond or sub-millisecond values, data ingested there, and you want to show the whole day. Then, of course, you do not want to show all millisecond space data points, but only a subset. I will copy the query. So you would use a query like this, which is which has the time bucket syntax as seen in the slides. So it says 50 minutes, so we would get one data point for all 50 minutes. We would get the location, office, office 2, office 3. We would get the count of values in the bucket, and max temperature and max humidity. And this for the last 3 hours. So if we execute the query now, we get 3 results. Why do we get 3 results? Because all data that we inserted so far is inside one 50 minutes bucket. So we have basically one bucket, which is for the start. For the start of the bucket is the time output. And we have 2 values for location office and 1 value for the other 2. Okay. So up to now, we did nothing special. And these are things that could easily be done also in IoTDB. And now I will show a little example why it's cool that we are in Postgres. For example, think about a situation where we say, okay, it's nice that we know the location of the offices, but we are interested in the countries where the offices are in, because one office or 2 offices are in Germany and 1 office is in Norway. And we want to know the average temperatures in German offices versus Norway offices, for whatever reason. And that's just a dumb example. So what we do now, we create another table, regular Postgres table, which we call locations, where we store the location of each the country for each location. So we insert some values. Okay, so the office is in Germany, office 2 is in Norway, and office 3 again is in Germany. Execute that for a second. Okay, so what I can do now is I do the query we did before, but Now I changed it a bit, as I do not longer take the location, but location's country, and I do a simple inner join on the location. I can execute this query. Okay, so I get basically the same result as before, but now with the country here, which is not so important for us here, but which means I did a regular join. And this is something very, very powerful. Of course, the example is not so intuitive, but this means, for example, in my time series above, where I store billions of points, I could use an ID for the location only. And all properties or tags I want to add to the location, I could add in separate tables, which makes my database way more efficient. Or later on, if I use some kind of flags, I could add a table to resolve the flags. For example, if I do not have humidity, or do have something like operation code, which would be, I don't know, an int or something. So this really gives me way more possibilities to model my database, as I do not have the very simple one-dimensional data models that most of the time series databases have. I can only add some fields or text to data, but I really get incredible options by doing the simple joins. Okay, so this is the very, very beginning of doing time series operation with Postgres, and now we go to a bit of an advanced example. Now we will talk about JSON-B, because something that you may missing is flexibility, because I have to define my full schema of the database upfront. So I have to say, okay, it's temperature and it's humidity. And when I have another office coming on where I do also measure, I don't know, the rainfall, then I have to change my table. And this is something which many of the NoSQL databases take differently, because they say, okay, that's just too much work to require the user to all of that. So we have a flexible schema. So I also talking about, for example, IoT devices. A new version of the device could have other data that they send, or you have different kinds of data sending to one database with different schemas. So you want to have more flexibility. So how do we achieve this flexibility? By using JSON-B. This is one of my favorite Postgres features, because basically it lets you store JSON strings in the database, but not in a way like you would use data type text, but in a way that Postgres understands it and can help you with some operations, or can do some operations in the database already. So I create another table, flexible series, which is regular table. Timestamp has a location, and it has the measurements in a JSON-B. Table, now it's there. And now again, I will transform it directly to a hypertable, because we do TimescaleDB here. Okay, it's a hypertable. Still works nicely together with the JSON-B. And now I will insert some values. So these are just some I will show them in a minute. So all I insert here is are arbitrary JSONs. So an empty JSON payload, one device which only sends temperature, one time I only send humidity, and in one example I submit both. So if we look now what's in the database, we start from flexible series, we see that we have different JSON strings. So far we do not take advantage of any of the JSON features. But what can we do now? We have the possibility now, due to the JSON-B support, to address fields of this JSON. So I can say, okay, give me only humidity values. And if I execute this query, then you see it here, then it returns always the field humidity if it exists, or null otherwise. Okay, well, it's not so elegant that we get null values, so I have another operator where I can say, okay, give me only those rows, only those rows where I have the key humidity on top level. If I could execute that, I only got those, so I would need to have the title. So this is a pretty nice feature because now I can say, okay, I want to operate on the humidity. And the object I get with the star operator is still a JSON object. So if it would have a substructure, then I could just go on like that. If I want to process the value, then I have to use this operator because then it is a string which is returned. So one situation to take care of is something like that. Doesn't make sense. I get an exception here as it tries to multiply 2 with a string. So I have to do an explicit cast here. So that's also something which you have to be aware of, that this operator binds stronger than this operator. So what we have to do, I'm just showing that because these are the pitfalls you start first with. So now I get this thing as text, then cast it to numeric, and then multiply it by 2. Okay, nice. So now I can really do math operations on a JSON payload. And this is something which is interesting in IoTDB, in IoT cases. Or I can use it, this is also important, I could use it in my where clause. So to say I only want the data bytes where humidity was above 85. This is a totally valid query, and it works. Okay, let me insert a data point like that. We see that it works. Query it. So now I get this data point. And this, because these are the queries you usually need to see if there was an abnormal situation or something. One or two other examples that I want to give you here is, for example, you have this database and you have no clue what all those devices send for values. So it's only humidity or temperature or whatever they send you. So you can also, with the JSON support, you can also say JSONB object keys for measurements from the series. I use the distinct operator because the JSONB object keys only returns me all keys that are in each payload, and distinct basically reduces them to a single cell. So you see, I only get temperature and humidity as a result. Okay, now going back to time series and TimescaleDB, I can now modify the queries we had before and write this query here, which says, okay, I have a time bucket of 1 minute, and I want to get the average value of the temperature, and only for those data points that have a temperature, of course. And this is the result now, and this now is a pretty powerful example, because one thing I get is I get the time series operation and the time bucket operation, but on the other hand, I'm totally flexible with whatever values I send. So if I have another device in operation which decides that it want to send speed because it's a car, it just does it. Probably I'm a car. It just does it and sends speed. And if I now decide, okay, I need to operate on the speed, then I can just add it in here and it works. So this is the one of our default approaches, because it really gives you the flexibility that you can do whatever you want and deploy. You don't have to redeploy and do a lot of ops, but only take care of the tables when you are already in operation. And yeah, other thing I can show you quickly is, of course, you can do more fine-grained analysis. For example, this is a query which counts the number of keys, of key occurrences in each time bucket. So basically, we could see if some keys are sent more often or less often, for example. You see, as you see here, just as an example. Okay, cool. So now we know a bit about flexibility and time series, and now our database grows bigger. I already prepared an example here. This is an example which is shown on GitHub, which will also be provided with the video. I also have a README file where you basically find all queries I currently do in the IDE. and I have a runtime which connects via JDBC to Postgres, creates a table I call flexible series 2, which is similar to the table we already used, makes a hypertable, and then inserts one database each second. And depending on randomness, it either has a value for temperature or for humidity, which is again arbitrary. And I just start up this example to generate some load on the database. So this thing will just start running and insert data into our database while we keep talking. Because now, for example, I can take this query here that we had before, just change the database to flexible series 2. And if I start the query, oh yeah, of course, there's no speed in it. There's only temperature in it. That doesn't work, of course. And now I already have to be careful because, let's do 1 day, because I insert multiple days in here. So if I leave it with 1 minute, I will get tons of results already. You can say 15 minutes. Okay. So this is what you would use, for example, for charting. Just get 1 value every 15 seconds. And that because, as you see, if I just add a count star, you see that I have about 450 values in each time bucket. The number varies because I only look at those devices that report the temperature, not all devices. Okay, so I may come at a point where my queries take too long, because if I currently I'm inserting several days, but probably I have a whole year, and then this operation may take long. So what can I do now? I'm in an RDBMS, so I use an index, of course. I said TimescaleDB already does its own indexing thing for time, but what we would like to speed up here is this lookup to see if the key is in there. And luckily, the Postgres provides by default a specialized index, a GIN index, which can be used on JSON-B series. So before I execute the index here, let me show you something. I do an explain analyze on this operation, and you see it already starts to take some time. So it's still operating. Because basically it has to look up all JSON values, although only 50% will match the condition. It has to look up all JSON values and compare them. And if I look into the query side now, you see one thing I see is it does a parallel sequencer scan due to the chunking of TimescaleDB, but it does a sequential scan over this condition. So basically that's what I said. It just reads every value, compares it, and then writes it back again. If I create this index now and execute the same query again, we will see how the output changes. So it's still running. Give me a second. So it still takes some time, but the index is already created. Mostly because it yields a lot of values, and I run this thing in the Docker container. But you will see that the output will now change, and it will, yeah, here we are. And it does no longer a sequential scan, but a bitmap index scan, which basically means it uses the index. You see the index condition here. So this is one of the operators which is sped up by an index. Before going on to another possibility to add more indices in complex cases, let's move on to data visualization, because I also wanted to show you how to visualize the data in Grafana. Because one advantage of this time series database is that they have a nice integration into visualization, and that's the same for TimescaleDB. So all I want to do is I want to start Grafana, which is linked to the TimescaleDB container. Just start up Grafana. I open up another browser tab, go to localhost 3000, and now I log in. Default is admin for Grafana, and then you have to override it. Okay, so first thing I have to do is to add a data source. And now the nice thing is that Grafana comes with a Postgres data source by default. So I can use this one here. The host is TimescaleDB, basically the name of the container. The database is Postgres, it's the default database. User and password are the same, so it's disabled. And here is a pretty neat switch, TimescaleDB, because it already has some support for TimescaleDB to do things automatically internally that you would otherwise have to do manually. So if I want to add a query, I already get presented all my times here. So I take flexible series 2. I have a column time, yes. Now I have to do something, or probably we start with conditions. That's easier. So now I can see, this is here you see the result of the query. Works out of the box. In my setup, with the JSON payload, of course, I cannot address it out of the box, but I have to say measurement temperature, for example, and this whole thing then has to be cast to numeric. Otherwise I can't deal with it. Okay. The editor is not optimal for the support here, but this is basically the valid query. Now I can re-query it. It says measurement does not exist. Let me look up. Measurements. It was called, sorry. Cool. Measurements. Okay. Now I execute the query again, and it does return. It shows nothing. Why does it show nothing? Because the data I inserted was starting from 1st March, I think. So what I have to do is to show like this year so far. Okay, this is now a really bad idea, and I mostly show it to show that it's a really bad idea because it will take some time, because I have no optimization at all. The only optimization is this time filter, so it only loads the time points in the database which are in this window. But now it will try to load hundreds or thousands of data points, which would be the case with no subquerying in place. So this is a really suboptimal idea and may take some time, and of course this doesn't make that much sense. So what I can do to avoid such a situation, we just let the query running. So what I can do to avoid such a situation is to go to flexible series again, and then add a group by, which is presented here, and it has this time interval none. And basically, this dollar interval is an internal variable of Grafana, which automatically adjusts the time range with regards to the selected window. So it will always change a suitable one. So you see now it already switches to an aggregate function. I again go into this query editor and say, okay, what I want is measurements temperature, but again I have to cast it to numeric. Okay. Can execute the query. Query works. And now you see it is quite fast. Let's see if the other one, the other one now finished. Okay, shitload of data points. If I zoom in, whoa, same misery. Again, tries to fetch, some thousands of data points. Here, the situation is different because if I zoom in, it will just internally, Grafana will change this, this time grouping for me, basically, and I will always get the appropriate bucket size, and appropriate in the sense what Grafana thinks is best for me. So I have already roughly constant set of data points which are fetched and transferred. So if I zoom in again, you see granularity is higher and higher. And then I have some limit. I think it's by default in seconds or something. But if I'm that deep in, then of course I could also skip the feature, because then I can just read the raw data points. This is something I wanted to show you because it's quite easy to work with TimescaleDB and Grafana. There's just some things you have to look at after one. If not, it's awkward. Okay, do we have some questions so far to the things I've shown you? An excellent question from Mehedi about the performance comparison between TimescaleDB and IoTDB. I have no hard measurements. I've not done a benchmark yet. I think the IoTDB guys did a benchmark. Basically, although TimescaleDB heavily improves what Postgres gives you by default, it's still an RDBMS. So IoTDB can heavily outperform IoTDB can outperform TimescaleDB with regards to speed. I would say factor 5 to 10, probably half an order of magnitude in some scenarios, but which is more important for us when doing edge computing, and also outperform it with regards to hard disk memory usage. Postgres is quite verbose or ad verbose as it needs to be, and the JSON format even more, as it has to maintain indexes for all keys. So if you're using indexes, then you need more storage than the plain text. For example, this question mark operator to work. And this is something that IoTDB can beat by orders of magnitude, so even 2 orders of magnitude, as IoTDB is heavily uses compression under the hood. So usually you can store in a real world scenario, you store a double value which has 8 bits effectively with 2 bits after encoding and compression. Using JSON and JSONB in Postgres would mean usually you spend more than 8 bits. So it's really 1 or 2 orders of magnitude that IoTDB can bring you with comparison to TimescaleDB. But as I said, TimescaleDB has other advantages that it has to offer. Hope that helps a bit. Are there other questions from the interested audience? One thing, I mean, we are basically done with time. If we have 2 or 3 minutes, if you have 2 or 3 minutes left, I can show you another short but really impressive example on how to basically migrate away from the purely JSON situation to a situation where I have 1 column per value. Because I see, for example, if I see an application, I usually only filter on this column and everything is slow to the JSON. What can I do? Is there interest in the audience? Yes. Oh, excellent. Some database lovers among us. Okay, then let me share my screen again. Okay, so sticking with the example we are already in, let's assume that we end up with a situation where usually I do a query like that. Hope you can see it. Let's just delete everything else for the sake of this. So usually I want to filter on temperature. This is something which I did not do upfront, but now I see that most of the times I filter on temperature. So what I have to do in my query is something like that, about 30. And this has really, really bad performance because I have no index here. And there's also no way in Postgres to put an index on that. I always have to read the whole JSON only this cell, but I only have to read the whole thing. And depending on the size of the JSON, this is pretty inefficient because I only need to read one double value basically, but read hundreds of bytes for the whole JSON or JSONB value. So what I would like to have is a separate column temperature, because then I can set a B-tree index on it and everything will be quite fast. But how to do this? And now we're coming back to the situation where I have a full-fledged RDBMS, which gives me all the tools I need. So what I do in this, or what we do in this setup, is we first add another column to the table. So author table, and the table in this case is flexible series 2. And I want to add another column, which is temperature, which is numeric. Okay, easily done. So now I have another column, easy peasy for a database system. So now, this is specific to Postgres, but works in other established databases as well. Now I create a trigger, and this trigger basically injects each insert command, which goes into this time series and executes a function for it. So basically this means whenever you insert a value, first give it to this translate function, or in the context of functional programming, I would call it map. Let me paste in this function. So I would say in this example, this is extract from JSON. So what I would say is, okay, whenever there's a value coming in, then read the temperature out on insert and store it in the column temp. Now let me execute both of these. So, oh yeah, I have to create this function first, and then I can execute this. Okay, excellent. So what I've done now is that from now on, whenever I do an insert with a JSON which contains temperature, then it will be filled automatically into the column temp. Yeah. Last thing which we have to do, of course, is the historic values, where I just say, call an update, an unconstrained update, and say, okay, for all values in there, just populate column temp. The only thing which looks a bit, oh yeah, here I only have to do single quotes. Up here I have to do double quotes. So okay, so this will probably take some time. Oh, sorry again, it's measurements. Oh, and up here also has to be measurements. I see. The crop function extract. So currently this would also, okay, I would have to delete all the trigger, but you get the scheme. So now I would update all values. So what I achieved now is purely transparent for my application. I now modify my queries to be filtered on a regular column where I can place an index regarding to my needs on. So I will gain 1 or 2 orders of magnitude in speed for queries where I say, okay, only where temperature is in specific range or something. Of course, this update script might take some time, even hours. We had a situation recently where it took 2 or 3 hours because we have really huge database. But the really nice thing here is that we have the flexibility to start with no model, totally flexible, and then introduce the model over time, only by doing database operations. And from now on, we're using directly this temp column, which are then 1 or 2 orders of magnitude faster than the old queries. But only because from my logs, I saw that this is a bottleneck. And this is a really nice flexibility that the whole Timescale Postgres ecosystem gives you in IoT scenarios, that you can see over time how things will evolve and then optimize when you need it, not at the beginning. This is what I wanted to show you, because this kind of closes the gap between, okay, but working with JSON is not optimal. And yeah, indeed, it's not optimal, but you can change your way whenever you want to, as you just saw, by just 2 or 3 database commands. Yes, basically that's it for the webinar today. I hope everybody took away something. Are there any questions left? Doesn't look so. Then I thank you for the attention, even for the overtime you stayed with me. Wish you a nice day, and whenever there are more questions, just ping me. Next week we will talk about Hono and show you how you get the same flexibility for connection protocols. So when that device comes which does MQTT or which does AMQP, or whatever, Hono helps you to narrow down this sort of connections. So thank you very much, and bye.